Greetings, everyone. Welcome. Thank you for joining us for the latest installment of our new Gleeble webinar series. Today's discussion will focus on new developments in the Gleeble platform and some coming soon items that we hope you will find interesting. Before we start, I do want to note that we have a series of sad events around the world with our global pandemic, protests and injustice here in the US, and the cyclone in India. We hope that you, your family, and your colleagues are all safe and healthy. And we also all hope that the second half of 2020 is a lot better than the first half. My name is Daniel Quigley. I'm the Director of Business Development and Marketing here at DSI. Usually I get to introduce our presenters and then I can sit back and relax. But after 5 weeks of that, our team thought it was time for me to do some of the heavy lifting and take a turn presenting. During the past month or so that we've been running these webinars, users have asked a lot of really good questions. And looking through some of those questions, we thought it made sense to take a step back, provide some history, a high-level overview of our systems, and where we are headed with some new developments. We also have some significant and positive company updates to share. For those of you who have joined for one of our previous webinars, you likely know how this works. But to new attendees, our goal will be to keep this webinar to 1 hour or less. If time allows, we will have Q&A at the end of the presentation. If you have questions, please submit them using the chat feature here in the webinar. As usual, we have some of our Gleeble All-Stars here with us. We have Brian Allen, Brian Smahoski, and Sean Garrity, as well as Fulvio Siciliano, who are here to answer questions directly in the chat during the presentation. Or we may be able to address some of the questions during the Q&A portion of the meeting, again, as time allows. We have a couple of hundred people registered to attend, so we probably won't be able to get to every question, but we'll do our best and we'll follow up after the webinar as needed. We will also make a video of this webinar available. I'll show you where to find that video in just a moment. We've made some changes to our website. And then finally, I'm going to go through some of these updates very quickly. If you have any questions or if you want more information, please reach out to me or any member of our team. We can point you in the right direction. Briefly review our agenda. I'll go through some sort of housekeeping items first, looking at some webinar information. And then I'll walk through some history, a quick company profile, an update, a very brief product overview, and then we'll get into the new products and enhancements, including some beta projects as well. We have 2 upcoming webinars. I hope you can join us for them. The next week, we'll have Dr. Fulvio Siciliano present Gleeble hot rolling and TMCP studies. That's a follow-up to a webinar that Fulvio had done a few weeks ago, which was very well received. And then the June 18th, Dr. Brian Allen will discuss strip annealing capabilities. I won't read the full description, but I will show you where you can find that information. On our website, Gleeble.com, if you click on resources, and then in the drop-down menu, click on webinars, that will bring you to this page. It's hard to read here, but on the page, you'll see an area where you can register for the next webinar. There's a brief description. And you can also register for upcoming webinars as well. And then at the bottom of the page, there is a description of previous webinars, as well as a link generally so you can watch that video as well. So we did think it made sense to take a step back and look at DSI, give a quick update. I won't spend a lot of time here. And I can't make a presentation without including this slide. It's so important to us. What is physical simulation? Most people listening in probably already know this, but I have to say it. Physical simulation of materials processing is the precise replication and duplication in the laboratory of the mechanical and thermal conditions that the material is subjected to in actual production or in end use. It's really what we're all about. The Gleeble system is a test machine. It's also a simulation machine. We do make a distinction between the two. In order to do this well, what's really important, what sets the Gleeble apart is the ability to do this very accurate measurement and dynamic control of really important variables such as strain rate, temperature, heating rate, cooling rate, and obviously thermal gradients. And then the real value of this is taking this data and taking it from the laboratory and applying it to the production process to inform your processes and improve your processes. So organizations that already run a Gleeble, they already know this. The Gleeble gives them an unfair advantage. The platform helps those organizations have better materials, more efficient processes, less scrap, more output, and much faster development times. A little bit of history on DSI. The original Gleeble was developed in the 1940s to study weld heat affected zone. And to this day, a lot of people even think of the Gleeble as, oh, it's a HAZ machine, it's a HAZ simulator. And it can do that, does it very well, but as you'll see, the Gleeble does a lot more than that these days. But we are proud of that heritage. That's where we started. The Gleeble was founded or invented at Rensselaer Polytechnic Institute by three researchers, Dr. Warren Doc Savage, Dr. Ernest Nippies, and Dr. Hugo Ferguson. And these three gentlemen are kind of legends in the welding space for sure. But to this day, we go to conferences and people will come up to us and talk about papers they read or classes they were students of one of these guys. And it really is impressive, and we're really proud of that heritage. We've also been exporting and installing machines for a long time around the world. And of all the questions we get, the most common question we hear is, how did the Gleeble get its name? And a lot of our longtime users probably already know this, but it is kind of an interesting story. In the 1930s and 1940s, there was a comic book called Doc Savage. He was the Man of Bronze. And it's a different Doc Savage than our Doc Savage. Dr. Warren Savage was a we call him the legendary researcher, but this Doc Savage was a superhero in a different sense. He's kind of a combination of a few different types of people. He was sort of an Indiana Jones plus The Rock plus Albert Einstein. He made this kind of the perfect man, and he would fight crime, and there are a number of movies about him as well. In one of those comic books, he created a machine that could do anything and called it a Gleeble. And while they were developing the Gleeble at Rensselaer, they used to name those projects, and they named it a Gleeble, and the name stuck. So it's kind of become its own thing. It's almost kind of become its own verb. So you can Gleeble something to dive in and to characterize that material. We have had a long history. If you look at that picture in the top left, that's one of the first Gleebles that was developed. This was obviously developed at Rensselaer Polytechnic Institute. The machines have come a long way since then. The next image is the picture of the building they built in the 1960s. That building has not come a long way. That picture could have been taken this morning. It looks almost exactly the same. But obviously what's happened inside the building has changed quite a bit. In the 1970s, we launched the Gleeble 1500, which really became the standard for these physical simulation systems. The 80s continued to advance those systems, starting adding computers to them. In the 90s, we introduced the 3000 series. However, the 3000 series that we produced then versus now are quite different. So the 3500, 3800 were introduced, and those machines have evolved over time, but added a lot of technology. Almost everything is new in them. 2000s and 2010s, we continued to add systems, add equipment, add mobile conversion units, which I'll talk about in a moment. And then we're only about 5 months into 2020, but it's been an interesting year for a lot of reasons so far. But at the end of 2019, DSI did join the VPG family. I'll talk more about that in a moment. That's been a very positive change. And we've already, we're working on a couple of launches here, the Gleeble 525, some MCU enhancements, the Rapid project, and the Cryoquench, which I'll talk more about today. So as I mentioned, we are entering a new chapter at DSI. We were acquired by Vishay Precision Group at the end of 2019. And VPG is an internationally recognized designer, manufacturer, and marketer of sensors and sensor-based measurement systems. And they specialize in markets of stress, force, weight, pressure, and current measurements. It's a very strong company. It's got a technology background, technology and engineering. They're an impressive organization. But what I do want to stress is that DSI, as you know us, a lot of that won't change. Dynamic Systems Inc., the name won't change. The team members that you know and trust will continue to be here to support you and your organization. In fact, we're looking to grow, obviously, and we want to have more people using the Gleeble and do things like we're doing today to outreach and work with our customers to support them. More information on VPG is available at vpgsensors.com. I do invite you to check them out. They are an impressive organization. And VPG and DSI both serve many of the same markets. So it's a sort of a natural fit. They're involved in the test and measurement, very involved in the steel industry, avionics, aerospace. So there's a quick profile here. I won't go through it in detail. But again, if you look at that global footprint on the right, it is a large organization. It's global. So we've seen a lot of support from them already, and we're looking forward to continuing to work with them and to grow the Gleeble business. spend a couple moments in just talking about our markets. I think it is interesting for our users to understand who else is buying Gleebles, kind of why they're buying them. If you look at our market, it's not easy to define who buys a Gleeble, who needs a Gleeble. You can look at it different ways. You can slice our market kind of across different criteria. One easiest way to look at it is industry. So obviously a lot of people on the call today are with the automotive or aerospace or the university, a lot of steel producers. So we sell a lot to a specific industry, but you also can look at our market based on materials of interest. So people that are steel experts or aluminum experts, titanium, they may use the Gleeble for a number of different types of applications across industries. Similar for, if you look at the applications of a process, rolling, forging, welding, casting, you may be a rolling expert and you may be in the automotive industry and focused on steel. So you can look at our market a number of different ways. Also looking at special initiatives. This is something where there is a large focus for an industry. So things like lightweighting, we hear a lot about that. I don't think that was a word years ago, but that's become a very popular topic. Additive manufacturing, obviously very important. New alloy development as well. One way to look at it is, any organization that produces or uses high performance metal products. That's kind of dumbing it down quite a bit, but that is really where the Gleeble can be valuable. So again, industries is the easiest way to look at our market. Looking at who buys Gleebles, this is interesting. Universities are our largest market by a fairly large margin, followed by steel producers, excuse me, and national laboratories. It's a little misleading. Universities a lot of times are funded by industry. For example, the automotive industry a lot of times will work with university partners to just do their research. So we don't sell a lot of Gleebles in directly to auto manufacturers, although that is changing. A lot of times they will partner with a university. So looking at where we're selling some of these other slices, these smaller slices probably are growing as well. If you look at this data, it's probably about a year old, but we are seeing more interest in end users, and we'll talk about that a little bit. Part of that is because we are offering systems that are a little bit smaller and more purpose-built for a particular application. I referenced these special initiatives. They really are important. We're seeing a lot of interest in additive manufacturing, powder metallurgy, lightweighting, and new alloy development. That's probably, those top three are really where we're seeing most focus. Microstructure evolution, some of these other ones they're kind of always there, always important. Whenever we see a hot new topic, it's money and interest are focused on those, but a lot of the underlying items that you are all researching are kind of always there. They're always really important. So I want to talk a moment about the 3000 series, just to give it kind of take a step up and look at the different models, what makes them different. It can get confusing when people will ask us, oh, how much does a Gleeble cost, or what is this machine? And it all really does vary. So I want to take a look at the three different systems in the 3000 series and kind of describe them. The 3180, that is it's kind of a standalone system. I'm going to use my laser pointer here. This unit, this is the load unit, and we call the pocket jaw, or the general purpose grips and jaw set is attached to the 3180, and it does not move. The 3500 and the 3800 can accept mobile conversion units, which are MCUs. We talk about that abbreviation a lot, so mobile conversion units. And this unit here can slide off, and you can slide on a different application-specific unit. And that's valuable because you can buy one platform and then use different. You can use a torsion system. I'll go through the MCUs in a moment. But one platform can really expand the number of different types of applications that you can use. The differences in these units, though, the biggest difference is really the force and speed. And I'll go through, I won't list all those specs right now, but looking at the 3800, for example, that's a 20 tons in compression. 3500 is 10 tons, 3180 is 8 tons. And so all the specs do change, but they all do have very fast heating capabilities. Looking at our mobile conversion units, I won't spend a lot of time on these. The Hydro Wedge is probably the most popular unit, other than the general purpose unit that comes with every Gleeble. The Hydro Wedge is used primarily to simulate the rolling process or forging, but it's multiple hits, high speed. It's a very powerful system. Gleeble hot torsion also used to simulate the rolling process, so the mechanics are different. This is one end is fixed and one end will rotate, and we can heat during rotation, which is unique to the Gleeble. The max strain, this is an interesting unit. This is again, the specimen will rotate 90 degrees and anvils come in from the sides and deform the material, and that can have unlimited. So you can put a lot of strain into a very small area of a specimen. Gleeble strip annealing, I'm going to talk more about that in a little bit. That is, we offer a mobile conversion unit. We call it the large sample strip annealing. It's basically a 5-inch by 10-inch specimen flat sheet that focuses on uniform temperature zone. There's some other strip annealing options as well that we'll review in a bit. The Gleeble ultra high temp MCU, that's similar to our general purpose MCU with improved cooling and some shield so that you can run high temperatures for extended periods of time. And then throughout all different types of Gleebles, you can do fatigue work. We have in the past offered a specific fatigue mobile conversion unit as well. A few years ago, we did launch the Gleeble 500 series, and there's been some confusion as to what this, where this fits in the larger product portfolio. This machine is a smaller footprint. A lot of our customers didn't need the full capabilities of the 3000 series system. They were more focused on a handful of tests, and they needed a machine that was easy to use, small footprint, less expensive, and can do all those things, but do them very well. So we launched the 500 series. It's been a popular system. This has our new touchscreen. It does, the Gleeble 540, which is a welding simulator, and the Gleeble 563. They're very similar. The 563 does add some compression capabilities as well. So it can be confusing when you look at a Gleeble. People do ask, well, how much does a Gleeble cost? That's similar to asking how much does a car cost. It depends on the model and what features you need, how it's equipped. So selecting the right Gleeble can be confusing. So I wanted to call out on our website, we do have a product comparison chart. It does help, even if you already have the system, just to say, hey, what exactly can this thing do? Especially as other people may come to you and ask for some work done. If you go to products on our homepage and scroll to the last item there, and that drop down is the comparison chart, and you can see there, it may be hard to read on the screen here, but you can see different factors in each machine, so it's all in one convenient place. We do also offer some specialty equipment. The Gleeble Lumet, this could be it probably will be a whole topic for a separate webinar. That's using laser ultrasonics to look at in situ at high temperature, looking at microstructures. So that's a impressive system. It can take weeks of testing, can be done in a single test. The HDS V40, that stands for the hot deformation system. It's a vertical machine, 40 tons. So you can see how creative we are with our naming systems. This is the only commercially available laboratory system that can simulate direct rolling from the continuous caster all the way through the rolling process in one sequence using a single specimen. So that specimen does melt. As it solidifies, anvils will come in and deform that system, and then you can simulate the rolling process. We will have a guest speaker in a few weeks. Our friends over at Warwick will be presenting. I think Carl Slater will be presenting this. They've done some great work on this, so that will be in a few weeks. And then the Gleeble Beamline, we've developed a custom system to work within a beamline. This is down in Brazil. So we'll dive into some new product developments. Again, we've been around for 60 years, or over 60 years. There's been a lot of developments over the years. One of them we introduced a few years ago. So this is new in terms of the greater scheme of things. The Gleeble Touch Control. So this is the console that is now shipping with new 3000 series. It is available as an upgrade as well. But here, this is looking at the new user interface. Again, that screen you see there is a touch screen. It's very easy to use. There's a range of enhancements as well. Again, usability, performance. We will say that we will always continue to support older systems, but as we look at developing new enhancements and developments, a lot of times they are going to be focused on the GTC. This is the future of control for the Gleeble, and if a lot of our users already do have it, I think they'll agree that it is easier to use, Training is a lot easier as well. So if you want more information on this, we're happy to talk about it. Some quick features on the new system. Again, I mentioned there's the touch screen display. One of the things that, again, our users, we've got a lot of user feedback on this, and what was most important to them was ease of use and finding the right information at the right time, information when they needed it to have that be presented to them. And then there's just the operation of the system is very intuitive. You can see some of the quick function panel, the lower control panel, and then there is some existing modules as well. So we always are interested in backward compatibility and do that where we can. Going forward, this again is available as an upgrade. In the past, we've used the existing console and upgraded. Now we'll ship an entire new console. It's a fairly easy install. And I'll jump right into a beta project that we're working on now. Again, customers always want the right information presented to them at the right time. And one of the things that they've asked for is real-time or near real-time visual representation of data during a test. So you can see here a couple of screenshots. You can see the stroke and force. So during a test, this would be updating live or close to live. So users can see what's happening. And a lot of times, this is useful for if you're talking to someone else that maybe doesn't know the Gleeble as intimately as you do. During running a test, you can kind of show them what's going on during the test. You also see if something is happening that shouldn't be happening. You can see that in real time, maybe make adjustments on the fly, or if you have to stop the test and start over. So this is a great time saver. It is also customizable, so you can change which features you're looking at. You can go to full view or look at a few different items at the same time. So this is something we're excited about. Our team did just get a demo of this, and it is really intuitive, easy to use. I think users are going to like it a lot. So in a couple of weeks, Dr. Brian Allen will present the Gleeble 525 and some strip annealing capabilities in the Gleeble. And I'm going to steal some of his thunder now and talk about some of these things. I'm sure he'll do a better job and go into more detail in a couple of weeks. But if you're looking at strip annealing in the Gleeble platform, you have a few different options. You can use small, flat specimens and standard grips. That's not ideal, but you can do some testing on sheet specimens there. We also offer the 2-inch strip annealing fixture. This is a popular unit. This goes inside the general purpose mobile conversion unit. And you can see the specimen there that in red, that's a 2-inch by 10-inch specimen. Again, we're focused on uniform temperature within that specimen. And then we also offer a large sample strip annealing mobile conversion unit. So that's a much larger specimen. It's 5 inches by 10 inches. Apologies for using inches to our non-US listeners. But we also recently launched the Gleeble 525 strip annealing simulator. And this is built on the 500 series platform. It's similar capabilities to the 2-inch strip annealing system. We always focus on controlled heating, controlled cooling, and focus on temperature uniformity. And what this allows is similar to that 2-inch specimen. It allows us to take a standard ASTM E8 dog bone specimen from that treated specimen later on. So the goal of this system is to be a little bit less maybe research focused and more focused on the production line, so that people can plant managers or someone that's running a line can take a specimen, run a test, get some actionable data quickly, and then go make changes on the fly in the mill. So Brian Allen will discuss this in a lot greater detail in a couple of weeks, but this is something that we're really excited about. We're launching this actually right now. This is, I think, the first time we're talking about this publicly. So this is exciting for us. About a year and a half ago, I believe, we did launch the Gleeble Induction. So for 60 plus years, we've been direct resistance, and we talk a lot about direct resistance, how that is, there's a lot of advantages to direct resistance, but there are times that customers or users will want to use induction heating. And so we have launched that system. It's quite effective. You can see an image here. We have a number of different coil designs. This is a plane strain test being tested. You can see pretty good temperature uniformity in that specimen. So here are some shots of what this unit looks like. As you can see, the induction unit will attach to the back of the Gleeble chamber. You can see an image here of the Anvil. This is just, we call this the head of the unit here with the coil installed. This is there's a number of reasons you'd want to use induction heating, particularly if you're using bimetallic or non-symmetrical unique specimens. Also, compression testing, so uniaxial compression. I think we did mention this a few weeks ago in our uniaxial compression webinar. This does offer some benefits. In particular, you can use Anvils that are not thermally conductive or non-electrically conductive, so you can really change the thermal profile or the uniformity across the specimen. You also have more control and the flexibility of where you're heating. You can move that coil a little bit, so that does offer some benefits as well. We've got a number of coils here to see large plane strain, small plane strain, uniaxial compression, and then you can do tensile testing or your standard 10 millimeter bar specimen as well if you wanted to do some different types of testing with that. So of course, heating, cooling rates, they will vary depending on sample size and material. So I can't share today all the heating rates and all those different characteristics, but as always, we can quench using air, water, mist, inert gas. And we have also introduced a new quench spray head system that can improve cooling as well. We use the thermocouples as always to measure temperature. This is compatible with 3500 and 3800 systems, but it does require the Gleeble touch control unit. As I mentioned before, going forward, a lot of our systems will focus on the GTC. I want to talk a little bit about a new project. This is I'm passionate about it. This is something that I've been working on a lot. It's the Gleeble Rapid Alloy Development Project. I'll walk through just a few slides here, look at our current challenge and what problem are we trying to solve, the solution, how we're going to solve the problem, and then just give an overview of some of the specifics of the RAPID program. RAPID stands for Rapid Alloy Prototype Investigation and Development. Pretty proud of that acronym. So the current challenge. So new alloy development is really important. It's, people need to have new high-performing materials. They need to solve key engineering challenges. So it's really important. The problem is it's really expensive and it's really slow. So once you have an alloy conceptualized, it may take a long time to produce a trial heat. It could take months to get that material in. Heats are usually very large in size, so that creates a lot of waste and inefficiencies. It takes a long time to then take that large heat, get it cut up into specimens, and get those specimens into a testing program. If the alloy's chemical composition needs to be adjusted even just a little bit, you may need to start the whole process again. And one of the driving factors for this was really that we talked to researchers and they were frustrated by the amount of time they were wasting waiting for each of these different stages. So they were waiting to get the alloy created. They were waiting to get the alloy machined down into specimens, and they were waiting for time on a machine. And they were wasting the productivity of a lot of really smart people, and that's frustrating. So we've worked on a solution to dramatically accelerate and simplify the development and characterization of new alloys. So the system will allow researchers to create a small amount of an alloy and then gather just initial performance characteristics. We're not fully going to characterize this material for years, but you can get some quick characteristics, and that you do that a lot faster. So you maybe have to take weeks or months using a traditional tool to do that. The system will melt, mix, and cast a small amount of an alloyed material, and that's measured in several pounds, and then apply a deformation to that material to achieve a more uniform microstructure, and then conduct tests to characterize the material. Pretty straightforward, but the goal is ambitious. A new alloy can be conceived in the morning and then created and characterized by the end of the day. And that is ambitious. For those of you that are working on new alloys, you may look at that and say, wow, it may take months to do some of these things. And really that's what we're trying to do, is create this system that can do all this very quickly. So just looking at the solution in a little more detail, the system will create an as-cast cylindrical billet. The billet can be reduced by rolling, or there are some other options as well. But to refine that as-cast microstructure, if you're not interested in characterizing an as-cast microstructure, the goal would then be to create a round bar that's about 1 meter long with a diameter of 10 millimeters to 13 millimeters. And for those of you that have a Gleeble or no Gleeble, you know that you can do a lot of really great testing with a 10 millimeter bar. If you have a 10 millimeter bar, you can do ductility testing, you can do dilatometry, compression deformation tests, so uniaxial compression. Cracking, so you can do the SECO test, which is kind of a Gleeble exclusive. A number of welding simulations. You can even do some torsion testing. So once we get that 1 meter long bar and we can machine that down, we can get a lot of data out of these specimens. So it is a modular design. This isn't a magic machine where you dump in a bunch of alloying elements and you get data at the other end. But it is similar to that. We just had to break it down into different modules and into a lab. The first module is alloy creation process. So we're melting, mixing, and casting. So we can take the input of alloying elements in a variety of forms, whether it's powders or chips or wire, raw materials. Go in, we'll cast that, and we'll have the output is a cylindrical billet. Module 2 is the deformation system. That billet is rolled down to produce that 13 millimeter bar. And that will, again, the goal here is not to simulate the entire rolling process. We'll never be able to do that with this rolling mill, but the goal is to create a more refined microstructure. Module 3 is specimen analysis. So it's very difficult to create an accurate casting under the best circumstances. It's even more challenging when you're talking about a very small casting size. We understand how challenging that is. It's really important to have your chemical composition analysis right there in the same room, right near your caster, so that you can get that immediate feedback and adjust your process as you go. We also want to be able to look at microstructure as you're going, especially the as cast versus the deformed specimen, to be able to look at that microstructure so you can make sure you're being consistent as you go into the later modules. Module 4 is a CNC system to basically take that 13 millimeter bar. There's some other cases where we use a larger bar as well, but then create those Gleeble specimens. So again, the importance of these specimens, that's why we're doing all this, is to get these specimens so that we can put them into a Gleeble and get our final data. So that's module 5. Is we're obviously biased, but it's the best thermomechanical physical simulation system in the world. And with these specimens, you can generate a lot of great data. So all these modules do come together into a single lab. It is really important to have all this equipment, this dedicated equipment, in the same lab. Talking to customers, a big problem that they face isn't the technical, getting things machined or rolled. It's all about scheduling. It's about kind of office politics of trying to get the right equipment, trying to get on the list, and waiting. A lot of times you're just waiting for all these different things to happen. The goal here is to have everything in the lab, available when you need it, to be very quick and get that data, to get those specimens prepared and get them processed so you can characterize that material as fast as possible. And the reason you need that data as fast as possible is really, if you look at AI, looking at getting more data into your AI models so that you can predict behavior. And the rapid system can generate this data so much quicker than current methods. It could take years to get that data. All right, I want to go through quickly some new developments that we're working on as well. This one is high temperature anvils. So uniaxial compression anvils have traditionally been limited to about 1400 C. And again, that's dependent on time, temperature, loads, the materials you're testing. But we have been testing new proprietary anvil cap up to 2000 degrees. It's early. We've got some more testing is required. However, it's very promising. Actually, the limitation isn't so much the anvil cap, it's the anvil backers, the sheathing, some of that kind of shell around that specimen. But 2000 degrees, it looks like that's it's been working. More testing is required, but you can look for something coming from us pretty soon. We're looking at starting to add part numbers and get those incorporated into our systems. Mobile conversion units are great because they let you take one platform and roll on, roll off different mobile conversion units and get different capabilities. For those of you that have used the Gleeble, you recognize that picture on the right. Those are super bolts, and you may look at them and they may make you angry because they do take a long time and they are frustrating. Our service engineers, certainly, they take MCUs on and off all the time. It's not their favorite part of the job, I'm sure. So we have replaced them with hydraulic crosshead locks, and these are available as a retrofit. They also can ship with new systems. When the system is powered on, you can see here on the bottom right, we have a small hydraulic pump that sits in the load unit. when the Gleeble is turned on, the locks are energized and you're ready to go. So that's really exciting. The other component of the mobile conversion units that we're trying to improve is getting them on and off and moving them. And these aren't the best pictures, I apologize. This is really a beta project right now. It's something we're working on. It requires currently a lot of force. It helps if you're a very large, strong person to move these things around and get them aligned. So we're working on a suspension system to make that much easier to do. I'll also talk about DIC, digital image correlation. So this, I think most people are familiar with this. A lot of labs already have DIC systems in their lab somewhere, maybe on other equipment. So I want to talk a little bit about integration of those systems. You know, if you don't have a digital image correlation system, we can sell you one, or we can. What happens most of the time, though, is labs already have one, and they come to us and say, "Can you integrate these cameras and this software with the Gleeble?" And I can't say we can do that every time. However, generally we've been successful with this. So I'd say, you know, talk to us about, you know, we can look at your Gleeble system, also your DIC system, make sure that it is compatible. But this, we really think this there's gonna be we're gonna see a lot more of this in the future. Looking at the Gleeble, how we measure strain, a lot of times it's a point-to-point strain measurement. What's great about DIC is it's really a whole field of strain. So you can look, it's like putting, you know, thousands of extensometers all over the specimen at the same time. So we think this is, you know, we've seen a lot more interest in this lately, and we think this is going to continue to grow. I think a lot of people will have DIC. We even considered making them almost standard with the Gleeble, because we do think they are going to be kind of the future. So we're going to see more and more of these. So just a couple of examples here. We put them high temperature speckle paint on the specimen so that the cameras can see that kind of the surface of the specimen and see how it moves. We have, depending on the camera providers, the camera manufacturers, we can get up to 1200 C. This one, the bottom right, is actually 1300 C, although we don't spec it that high, although it did work. But DIC at high temperature does present some challenges. So looking at how we integrate DIC is interesting. So we use obviously some software hardware connections to help integrate the systems. We have a jaw rotation kit. So if you're using a flat specimen, you want the broad side of that specimen to face the camera. So we'll rotate the jaw. We have a jaw rotation kit. But maybe most important is the lighting package. When you have that emissivity, the bright color of the specimen, the images can get washed out. And a solution to that is basically throwing a lot of intense light at it. So we've developed these blue LED lights, and that improves performance and lets us test it and measure at higher temperatures. You can put these cameras in the front of the Gleeble. You can put them vertically or horizontal, or you can put them in the back of the camera. Okay, if you put them in the back of the camera, you just have to be careful of that intense light that I just mentioned. If you walk up and look into the vacuum tank, you may see a blue light for a little while. So obviously be safe, but putting the cameras in the back is helpful, because you can open the tank door and load new specimens in without moving the cameras and realigning things. Another feature we've added is auto darkening glass. So if you have looked at a bright specimen in the past, you know that it's not always wise to do that. You want to be safe. Here we've borrowed some technology from the welding industry. They've developed this auto darkening welding glass. It's actually adjustable, so you can change shading level and sensitivity, and it does slide in and out as well. So you could put in the traditional glass darkening glass as well. So this is nice. It's a nice little feature, and I believe this is operational, so this is available now. Another project that we have been working on is Cryoquench. Over the years, Gleeble customers have inquired about the ability to quench specimens at below room temperature using liquid nitrogen or other chilled mediums. There's a lot of applications where this is of interest. In several cases, Gleeble users have actually developed this on their own, independently of us, and they've had various levels of success. To date, we haven't offered this as a standard feature. We had some safety concerns. People may not have been using the correct plumbing and the things that may not rated to the right temperatures. However, interest has been high, so we have been diving into this and working on it. One of our engineers, Nick Bloomling, has spent a lot of time on this. He's done a great job. We're doing this so we can do it safely and reliably to achieve this cryogenic quenching. So you can see here, you can see that specimen, it is an ISO-Q specimen, and it is, obviously you can see that it's cold. We have, here's some data. So this test, we went from 1100 C down to -175. Again, you can see some of the setup information for our Gleeble users. That makes sense. You can see the specimen type. Again, we use ISO-Q method, stainless steel grips. It was a 10 millimeter full contact specimen. We went down from 1100 down to -60 C in 12.5 seconds, and 26 seconds we went down to -172. So I think that's pretty impressive. I will say it's important to note that the goal of the Cryoquench system is to achieve a low temperature, cryogenic temperatures. This can be done quickly. However, the goal is not to accelerate cooling rate. Our traditional quenching feature works really well, and arguably better than this. So the goal here isn't speed, it's just getting down to that temperature. Although what is fast, I think that is still a pretty fast cooling rate, but that's all relative. We are also working on testing some non-conductive materials. I don't have a great image to share with you yet. We're still working on this. This is in beta phase, but we are developing equipment to test non-conductive materials. So the Gleeble is best in class for high temperature testing. For room temperature testing of non-metallic materials, I don't think this is going to replace your standard Instron or MTS universal test system. However, if you have a Gleeble and you are interested and you want to be able to test other materials, that's a question we get a lot. So we are working on some gripping, fixturing, as well as methods to heat those specimens using a susceptor or some different options, both heating something around the specimen. So there's some interesting methods that our team is working on now. We'll continue to work on this. I don't have a launch date yet. Hopefully we'll develop this quickly and have something later in this year to discuss, probably at a user meeting or maybe another webinar. We've also made improvements to our Hotzone transducer. So those of you that use the Gleeble and you use the 39060 HZT transducer, I know our service engineers don't like that unit. It's got some issues. It's difficult to install. There's only 2 gauge lengths settings, and there's some measurement error when you're changing alumina rods or you're replacing it or moving it. So some of our engineers, Jonathan Underwood, has been making some improvements to this. The new design will have a new part number. We'll announce that soon, although it's 9665-001. It's not in production yet, but it will be soon. It is much easier to install and mount. It eliminates that measure I referenced, and it's unlimited gauge length capabilities. So it does. You can see how it's clipped into that unit a little bit different. So this is something we're excited about. I know our service engineers do appreciate that change, and I think our users will as well. Just a few more slides. One of the things I want to talk about here is some new support resources. On our website, the first thing to reference is if you go to our website, you'll notice there's a live chat feature. So if you have a quick question, you can go there and you can chat. And there's a few of us, including myself, that will field those questions. And we may need to point you to the right technical resource if necessary, but feel free to use that. We'd love to connect with you. Also, if you go to resources, I already referenced that there is the webinars link. Hopefully you'll continue to check that out. But also there's the customer support portal. This is very, very useful. If you click on that link I just showed you, or if you go to support.gleeble.com, you'll come to this page. The first step is to create an account. Currently, this is for current customers only. So I'd ask you when you sign up to use your work email address. That way we can make sure that you do actually work with that organization. So you'll create an account. Within about 24 hours, you should have access to the system. Depending on how this webinar goes, I ask for some patience because the guys may get a lot of requests coming in. But once you're in, you can then go to the knowledge base and search for information to help you, or you can create a support ticket. Once you, here's an example of the knowledge base article. They've done a really good job. You can't read this, I apologize for that, but it's a very long page, there's a lot more data. But one of the things that they do that's really nice is they have these troubleshooting flow chart. So if you're having an issue, you can kind of go through and a specific task, okay, does that work? No, and that is really useful for trying to self-diagnose some of these problems. If that doesn't work, you can create a sample, a support ticket, and here's a sample of that. If you create this ticket, it will get assigned automatically to one of our service engineers. You can see this one was assigned to Brian Smahoski, but our service engineers usually are traveling. They're around the world. They may not be available. So this ticketing system will get your issue to the right person at the right time and make sure someone can get you a response quickly. Finally, I wanted to just mention that, unfortunately, most technical conferences have been postponed or canceled due to the pandemic. But conferences are a great way for our team to interact and collaborate, innovate with the Gleeble community. These webinars are a nice way for us to connect, but it's not the same. We do miss seeing all of you face to face and look forward to gathering again soon. But in the meantime, we'd love to see some of your papers. So if you can send us your research papers, we do have kind of keep a library here. It's nice to know what people are working on as developments come along or potential collaborations, we can share that information. So if you have paper or research that you're working on, please send it to us at research@gleeble.com. We'd love to hear what you're working on, and also just it's always great to connect. That is the bulk of my presentation. We do have some time for Q&A. I've asked Brian Allen to step in. I know there's probably been some questions I haven't been able to pay attention while I've been presenting. So Brian, do you mind hopping in here and perhaps selecting a couple of questions that we can address as a group?
Sure, Dan. Thank you very much for that presentation. So I've noticed a few questions on the question board, and I think most of them have been answered in general, but I think it may be useful to expand on a few of them. There were a couple of questions about what is available with the induction heating. So as Dan mentioned, we have introduced a new induction heating system for the Gleeble. As you all know, the Gleeble typically has used direct resistance heating to directly heat the sample, and that is very beneficial for a number of reasons because it heats the sample very quickly, it heats the surface and the center at the same rate, and it can generate high thermal gradients in the sample to simulate things like heat affected zones. But there are times when you may want a very low thermal gradient, and there are some experiments where you may want to actually just simulate the results of induction heating. So we have added this. As you all know, the induction heater does require a coil to go around the sample. Now that coil does take up some physical space inside the vacuum chamber. So a couple of the questions asked about, can we use a water quench with the induction heater, and can we use Hotzone clip-on extensometers with the induction heater? So the answer to the water quench is yes, we can, although we will have to make sure we have an appropriate coil design. Depending on how we position the water or gas quench, obviously the coil can produce I'll call it a shadow around the sample that would prevent the quench water from hitting certain parts of the sample. But by positioning quenches from either the ends of the sample or using what we call a split coil, which is essentially an open center coil, but still has a uniform field that will heat the sample uniformly, we can do the water quenches. The Hotzone extensometers are a little more difficult. Right now, we don't have any coils that we would necessarily recommend a Hotzone extensometer to be used with, but there is the possibility to do different kinds of coil designs. The most efficient and probably the coil that gives you the most uniform heating is a helical coil around the sample, but there are such things as split coils, one-sided pancake coils, axial coils on two sides of the sample that potentially could allow you to do things like Hotzone extensometry and digital image correlation analysis with the induction heating, although there'd probably be a little bit of coil development work that would be necessary to do that. There's a question here I see about the temperature range for the induction heater. The temperature range for the induction heater would be the same as the temperature range for the standard Gleeble. We peg that temperature range at 1,700 degrees Celsius. Typically, we do that because of the heat load in the tank. So that is what we definitely can guarantee that the Gleeble will do for normal sample sizes, although we routinely have customers that exceed that with smaller samples. samples that won't put too much heat load into the tank. So we can do that as well with the induction heater. The coil itself is water cooled, so there's no problem with the coil overheating as long as you have the grips set up so the grips themselves don't get too hot. Really the only limit on the temperature of a sample being inductively heated is really the same as the limit on the temperature of a sample being direct resistively heated, and that is either the temperature of the grips or the internal temperature of the tank itself. So,
All right, Brian, this is
okay.
Dan again.
Yep.
Looks like there was a question about kind of comparing the rapid system to the HDS V40. I did go through the rapid system fairly quickly. I think the rapid system again is really the goal there is creating that specimen. And I think what we'll hear from Carl Slater in a few weeks from University of Warwick, they're actually doing very similar things. And they have an HDS V40, and they're also creating those specimens using a similar but larger casting system as well. So the differences are, I think the goal there is the first several modules anyway, is creating those specimens and getting those specimens down to a testable form quickly. And then, so you could, but one of the ways you could use the systems together is to create that casting. Maybe you don't need to deform it. It could be as cast, considering you're going to be melting that specimen again in the HDS V40. I'm not sure if there's anything you'd like to add to that.
No, that's I think a pretty good description. One of the things I will say is that at least in the current iteration of the rapid system, we are casting round bars, although I don't see any reason we couldn't cast any shape we want. The HDS V40 typically uses a sort of a rectangular shaped sample, but there's certainly no reason we could not provide different molds for the rapid caster and cast those those rectangular bars. And since the general goal of the HDS V40 is to test the as cast structure, you may or may not need any kind of a breakdown mill involved there. I think your cooling rate's probably fast enough on the smaller samples, even what we would consider in the Gleeble world a pretty large sample, the 10 millimeter by 40 millimeter that is often used in the HDS V40. I think you could probably just avoid, for the most part, for most experiments anyway, any kind of a breakdown mill in the intermediate step. So yeah, I think they would go together. One question we do occasionally get, because we can melt in the HDS V40, it is a direct melting and casting simulator, and we do get this as well in some of our melting simulations that we offer in the 3800 and 3500. Is can we alloy directly in the Gleeble? The answer to that question is kind of. We can obviously add some elemental wires or powders either onto the HDS V40 sample or into the quartz crucible in the melting setup in the 3500, 3800. The problem is that we don't have a way to control exactly the size of that melt zone. So it would be a little bit of a shotgun approach. I could certainly add some elements, melt them in either one of those systems, cast them, and then get the properties and then analyze that later. But I couldn't ahead of time tell you the exact amount of alloying element that you would need to add to get a precise alloy mix in the sample. But most of the time when you're doing alloy studies, you're looking at 5 to 7 data points over a range. You're constructing a fit curve between the properties of those data points, in which case you may be able to get something very useful from a in situ alloying in the HDS V40.
Great, thanks, Brian. So we had a question here. It looks like there's a question about a Delatometer experiment. Can you do it for up to 144 hours? Maybe let our service engineers answer that. I will take an attempt at it. The short answer is yes, but there's a lot of things that can go wrong in that time. So I would definitely budget extra time, double or triple that. So if you have a lot of those tests lined up, it could take a long time. You may get through 142 hours of it, and a thermocouple pops off. So that may drive you crazy. And then there are some, the system needs to be really kind of tuned in and dialed in to make sure everything is operating correctly. But I think Brian Smosky, or one of you or your team, maybe you can answer that question in the chat as well. Yep. And thank you for doing that. Let's see, we probably have time for one more question. Brian, is there one that you'd like to cover here?
I'm just looking through some of these. I don't necessarily, looks like we've got most of the questions in the forum answered. There's a question here about, does it show the thermal gradient or profile? And I'm not sure if that refers to the induction heater or what that refers to, but I'll go ahead and try to answer that, assuming that it's in reference to the induction heater. And yes, we can get the same thermal profile in the induction heated sample as we would with the direct resistance heated sample, which we typically do by adding multiple thermocouples to the sample. So we are able to, with the software, to filter out the induction heating noise from the thermocouple signal and get obviously a very good thermal temperature reading. And we can then definitely create a thermal profile or a gradient based on, wherever you want to put thermocouples on your sample. One of the things about the thermal profile in an induction heater, and I think most people that use the induction heater are trying to minimize the thermal profile. They do not want to lose heat to the conductive anvils and grips like you typically do in a direct resistance heated is a big reason to go with induction. But you could tailor a coil with any geometry you want, and it may take some trial and error, but theoretically, create a custom thermal profile in a sample with the induction heater if you want. So I guess the answer to that is that yes, we can create a thermal gradient with the induction heater as well, if that is in fact what you want. Although usually the opposite is typically the goal of induction heating.
Great, thank you, Brian. So I think that does that's all the time we have. So as always, we want to be respectful of everyone's time. Unfortunately, time is up. So this is where I usually thank our presenters, but it'd be weird if I thanked myself.
Well, I will thank you, Dan. So we appreciate the presentation and the good information, and we will certainly thank all of our listeners for tuning in. We know you're all very busy. You all have a lot of things to do, so we do recognize that your time is valuable, and we do appreciate that you've chosen to spend some of it with us.
Well said, Brian. Thank you. So if you have technical questions on the operation of the Gleeble, please contact our service team. This would be a great time to create an account at the service portal I referenced earlier, create a support ticket. However, as always, you can contact them by emailing service@gleeble.com. If you have any questions about how the Gleeble can support your research, please email me or any member of our team, Brian or any of the guys on this call here, but we will connect you with the application expert to find the right solution. My email address is dan.quigley@gleeble.com. It's there on the screen. Feel free to reach out and I can point you in the right direction. Again, thank you for joining us. Everybody, please stay safe and healthy. Have a great day or evening.